SLB is the world's largest supplier of energy services, which, because the world depends on oil and gas primarily, then this largely involves drilling wells. So we don't own any energy fields, but we're the people and the equipment and the technology that work in oil and gas space. And so what I'll do is I'll introduce the company and what we do, and then how explainable AI fits into what we do, and in particular the work of my group. And then we'll talk a little bit about internships we've had in recent years and the opportunities that we have. So first of all, the context. The world obviously relies heavily on energy for the basics of food, shelter, and warmth, and relies very heavily on oil and gas. So the challenge that we have going forwards between now and 2050 is the energy use per person is going to continue to increase as more and more people are lifted out of poverty, essentially. But at the same time, we're in a position where the climate is already being affected by the amount of CO2 emissions, and that is going to get worse before it gets better. So here is the picture of what is likely to happen for the carbon emissions. So at the top left corner, you can see a little dip. That was the effect of the pandemic. So even with everybody staying at home pretty much all the time, the world didn't really dramatically reduce its emissions. But we're in a position where the technology will allow that to happen in the coming years. The part that's colored in solid blue is the actual amount of carbon the world can afford to release to avoid the 1.5 Celsius increase, which is the one people see as, you know, the tipping point. And then the hatched part shows how the world is essentially going to miss the target. And you'll have heard recently the person who founded the Green Party saying he thought it was too late. We absolutely agree. But the world is on a path to potentially on a path to get to net zero in 2050. And then the hatched part underneath is the amount of additional over injection of CO2 that needs to occur to the end of century to meet the Paris Agreement. So to limit 1.5 Celsius over the rest of the century, whilst at the same time allowing this increase in energy use to as more people are lifted out of poverty. So within that, as a company specifically, every company, well, most companies now will have their emissions audited. Scope 1 are things you do yourself. Scope 2 are the products that you use. And then Scope 3 is the actual impact your company has on the emissions. And if you work in the energy industry, as SLB do, then your Scope 3 is going to be very big compared to your Scope 1 and 2. And then this shows where we are. So the total is coming down. It needs to come down at roughly the pace it is coming down all the way until 2050. So now we get more to the details of what do we do. So the things we do are helping industry decarbonize. This is largely kind of emissions capture and storage. Helping oil and gas minimize the emissions they make. So the biggest commitment right now is on methane emission reduction. And there's already lots and lots of things technically that can be done to mitigate that. So between now and 2030, that's kind of most of the gains that you'll see will be in reduced methane emissions. And then there's new energy systems. So this is the storage of energy as hot water, batteries that are not lithium-ion batteries, so kind of static batteries, which are needed as you rely more on solar and wind, which are intermittent, you need lots of energy storage. Because, for example, in the UK, we typically aren't using our energy when it's warm and sunny in the daytime, but we're using it on cold winter nights. So there needs to be a dramatic increase in the ability to store the intermittent sources. And then there's a big focus on getting technology out quickly after it's developed, simply because, of course, time is against us. So now we get to what my group does. So we're the automation and planning research group. So this picture is from an article in Medium that talks about all the different types of AI. And the reason we like this picture is because it's much broader than most articles on AI. We're mostly focused in my group on what we call machine reasoning. So planning, scheduling, semantic web, and probability-based methods. We have another group that's focused on what we call data-driven, which is the machine learning and reinforcement learning. In the case of the planning and scheduling, there's a lot of existing algorithms. People who do computer science degrees will be familiar with A** and various search algorithms. So why do we still do research in it? And what we find is that there are nice algorithms for specific cases. And then there's a tendency to try and fit your problem into one that you know how to solve and then solve that one. Whereas in real world application problems, they don't fit into the neat algorithms that are available. In this picture, high quality algorithms exist in the corners of the triangle, but most of our real world problems are somewhere in the middle. So this is about automatic analysis of problems to break them down and create solvers that can solve them directly. The other area we do a lot of work in is Bayesian networks. So this is because we can take knowledge from our engineering teams and structure it into kind of cause-effect relationships. But this is where we get to our issues with explainability. So the nice thing with the Bayesian network is you can specifically say what each of the probability nodes is if you want to define them all as concepts. But then the answer in this case is my well borehole full of chippings so that the drill bit will get stuck, and the answer is 70%, then that's actually of not much use. And the explanation that all the numbers are in all the boxes is also of not much use. Engineers need kind of directed information that focuses them in on what are the root causes, what should they be thinking about. So this comes to the first of our explainable projects. So this, what you see here was generated by an intern who was doing an iCase PhD for us with Heriot Watt and Edinburgh Centre for Robotics. And so she looked at the generation of explanations for a Bayesian network. How much of the Bayesian network to show the end user, how to turn the paths through the network into human readable explanations. And then she did a 6-month internship where she focused on kind of our problems and produced a system which is now used in Mexico. It's used by the geothermal, Star Energy geothermal company in Indonesia. So it's used basically at quite a few locations around the world. And they're generally using it to understand, given where they are in a well operation, what is the risk that they will get stuck, which is a very expensive, it's very expensive to get unstuck in drilling, particularly geothermal wells. Another example is explanations when we have planning and scheduling. And this is really the one where we've proposed a PhD with Simone, in your department. And this is when we make a forward plan, and on the left-hand side, there's a schedule, and on the right-hand side, there's a plan. So the difference with the schedule is we've got tasks, and we need to allocate the people and the contractors and the crews. But it turns out that when you plan for a 5-year period, then people are inherently optimistic. So although you can use an algorithm and it will strictly put all of your equipment that you have and schedule it, that would be a much longer timeline than the one people normally aim for. And this is, I'd say this was quite challenging for us coming from physics and engineering background, that we were generating plans and people weren't happy with them. And so if you look at the bottom here, and you'll see there's a little bit of red on a kind of histogram chart. The red occurs where we know they only have 6 crews to do this particular operation. This schedule you're looking at exceeds that, using 7 or 8 crews at various points along the way. But it turns out that this is the kind of plan that people want to work to. Because in reality, this schedule is interlinked with another schedule, which is to do with the availability of people, availability of equipment. Those things can change over time. So you don't want something that's very rigid and completely mapped out when you know that there are neighboring projects that you might be able to share with, and there's kind of crossover. So we need to really understand this bias that people have, which is known as the distance bias, and how we should be generating. So beyond just explaining what the plan is, we need to generate plans that are consistent with the way people like to behave. On the right-hand side, and this is quite common with what we call planning. So with planning, we're really talking about what are the list or order of events that need to be performed to achieve an activity. And in a fully automated system, like a robot, then this works very, very well. As soon as the plan is for a robot and a human together in an activity, which is quite often the case for us with drilling, we get into a problem that people have done the job before, they have a way they like to do it. Why is what the automated planner telling them to do better? And quite often it can just be different and not better. And so we characterize this as why not do it my way? But basically, there's a whole area where people are quite justified in saying, why should I do it the way your computer's saying to do it versus the way that I want to do it already? And so there's a whole area now that we're quite good at having AI help create decision information. We need better ways of it supporting the people who make the decisions and kind of allowing them to almost argue with it in the way that they want. And this third example is one that an intern's going to do for us this summer. So it's quite popular to try and replace nonlinear physics algorithms, which are kind of slow to calculate, with fast approximations. But the problem with fast approximations is that they can end up being like a lookup. So although they have very reasonable performance on individual answers, they don't have any formal properties on the far side. So, and this is a student from Heriot-Watt, and she's looking at how we can define verifiable formal properties during the training side to guarantee consistency. So the example here is thermodynamics. So Maxwell's relations basically mean smooth derivatives. And when we do a fast approximation, we want a fast approximation that has smooth derivatives. So this last example, this is an iCase PhD we're starting with Huddersfield in September. And this comes to why we're interested in this explainability and human biases side of planning. So here is an example of a typical job that we do, and we have tools that go around the world, and then we have resources, and we have people who have day-night schedules where they need to have their rest periods, and we have automated plans generated, and all of these things are interlinked, and people know that they're interlinked. And in general, the AI at the time when it's making calculating a plan or generating a decision doesn't know about the rest of the world and how everything's interlinked. And so what we're doing in Huddersfield is figuring out how we can connect these things together so that one solution kind of ripples through for other solutions to find out about it. But then in the Social AI group, the one we've proposed is more to look at the psychological side of how people with more knowledge, or rather broader knowledge, will interact with these more localized optimizations. So with that, I'll stop showing slides and just talk a little bit about internships that we do and how best to apply for them. So in general, internships we do with PhD students are 6 months. And typically you do it by taking an extension inside the PhD. And the reason we prefer that is we might ask you to work with data that you're not allowed to then present in your thesis. Or we might not, like as a maturity level of what you've done in your PhD might actually be too far ahead for us. And then you find out we just need some kind of earlier stuff that you'd learned about in your background reading in your first year. And so what you do for us may not qualify for a chapter in your PhD. If it turns out that what you do is suitable for a chapter in your PhD, then we try to find a way to make sure that you can include it. But we stick to the extension system. So essentially you come to us and we employ you for 6 months, just so that just so that risk is clear and it's separated. When it comes to applying, what we're interested to know is the topic of the PhD. We're quite good at understanding opportunities kind of for knowledge capture. So what we struggle with is a lot of people's CVs don't give enough information about the application of what they do. So you'll quite often see a list of places people have worked, skills that they have, which are relatively common across candidates because all the candidates are applying for the same position. And in general, you can quite quickly determine the small number of candidates who just haven't got the right background. Most of the candidates are applying, and then the risk is that all the CVs are essentially similar, and it's very hard for us to determine what's different about the candidates, what they're bringing, and what their specialist kind of knowledge is. So I would suggest focusing on almost in a personal statement what you think the real world impact of your PhD might be. That kind of thing tends to stand out with candidates. And don't be kind of shy about promoting what you did as being valuable to industry. There's it's hard to describe, and I'm sure I was the same when I finished my PhD, but it's almost it's helpful if it's presented in a way where you kind of say, I'm really interested in this because there's a fantastic opportunity to make things better in this particular regard. And then if one of our scientists sees that and then thinks about their own work, thinks about the issues that the users of their algorithms and their work run into that potentially could be solved, then that's really the key to us being excited about an internship. So I've got a few minutes for questions if people want to.
Okay, thank you. Thank you very much.
Thank you so much.
Do we have questions for Michael? So maybe I can pose a question just to break ice. What do you think is the best value that the students bring back when they go back to their PhD after an internship at your place or more generally in industry?
So I think what they bring back is an idea of both the value that they're creating in their PhD, which is, I mean, in general, it's way beyond an academic value that you're creating, but it's hard to appreciate that when you're close to it. And also maybe how hard it is to bring something to industry. So a good example was that example of the explainable Bayesian networks. The student had done a huge amount of background work into what kind of explanations people need to hear. And then because the audience was well engineers, she set up like a webinar to explain her work. And this was global. So we had people from like 100 different countries involved. And then she developed a questionnaire for them to express their preferences. And that side of it was very useful because previously she'd done this work kind of locally with UK-based people, most of whom would be first language English. And then our audience is largely second language English, although English is the language of the company globally. And then this informed some of the thinking about how we generate these things. And so there, I mean, her work was able to have a relatively big impact in a relatively short period. Other pieces of work, we learn halfway through that actually it's not practical. That's still okay. One of the reasons we have a research center is so that we can try to apply work from universities and kind of assess the readiness level. And so a good example of work that's not ready today is we've had an effort looking at whether quantum computing can solve scheduling problems, because all over the internet you hear that it can. We have a nice set of benchmarks that, so we'll know when it can solve the kind of problems we're interested in, but the ultimate result of that was, you know, maybe next year, maybe in 2 years' time.
Yeah. Okay, thank you very much. I don't know what is your availability with time. I don't know if there is maybe in the meantime.
If you've time for one more, so just in terms of employability after finishing the PhD, I don't know if you're able to speak to this, but do you find that PhD students who took some time out to do an internship, like the kind that you're describing, are perhaps stronger candidates, or is it really just the quality of research at the end of the PhD that matters, if, say, someone was going into industry or into academia?
So I would say it'll depend on what you did before a PhD. But if you were straight through school, college, PhD, then having industrial experience is the thing that you will be asked about when you come for interview. So employers are very interested to know any experience with any kind of work tends to stand out on a CV, which sounds peculiar, but even though you've dedicated your life to, passing the exams, getting to the place where you can do the PhD, and then producing this piece of work that moves science forwards a step, the people who are interviewing alongside you have all done that. And so employers tend to focus in interviews on those little things that you've done that other people haven't done. And so an industrial internship is an example of that. But even non-industrial work that you did as an undergrad to pay the bills, it's worth having a story about how that describes you as a person from the point of view of employability. And in employability, I mean, the key things are just the usual soft skills of showing up, being interested, joining in with everybody else. And so, yeah, I'd say the value of it for post-PhD employment is largely that you will be asked about it at interview, and you'll have a story to tell about applied research, which comes from direct experience. And that really is where the value is, I would say.
Thank you very much. That's very valuable
Mike, I
insight.
just have a final question. Do you have a rolling scheme for internships? Can people apply at any time, or do you have a particular call, because it's probably just more like a practical information for our students?
Yeah, so SLB as a whole has a rolling call.
Okay,
in my group directly, we typically have 1 or 2 each year, and people can apply at any time. You can apply through the central SLB careers website, but it's worth at the same time on LinkedIn finding the right person. So if the right person's me, email me and say I'm applying, because that way, because we end up interviewing and kind of finding our PhD interns locally. Whereas a global company has obviously this central global system. It's easy to get lost when they're employing 5,000 new mechanical engineers as the one PhD intern in explainable AI, for example.